Am I live? Am I live? I don't think so. I am, kinda. Hello. No, I'm not. Maybe I am. Who knows? Who knows? Hello, Sorbet. Am I even live? What is going on here? I can't see anything. Look, I'm really good at this, ain't I? Got this all down pat. This is 13 weeks in a row I've been doing this. I know exactly what I'm doing. Perhaps I'm up? Hello, hello, can you hear me? Hey, there we go. Alright, that's working reasonably well enough. Let's just pop this out and get ready to go. Glad to see you here, Sorbet. You didn't miss much last week if you didn't catch up. We're just talking about error handling a bit. Where's my channel on YouTube? It's nowhere. That's really kind. I'm very glad about all this stuff. I can't see anything. Hello, hello, hello. Oh, that's long. I see. You can hear me now. That's good. Greatest apologies for this. I don't know what's going on. This is a very strange situation for me. It's just getting black on some of the outputs. Sorry, I'm just getting YouTube up for a moment in case we get some rando in there. Be cool to see somebody, but it's incredibly slow right now. I guess my explanation for the situation here is that I am just waiting to see if anybody else pops in. It's not my own incompetence, it's a tactic. Here we go, I'm currently live here. Watch like cable TV. It's asking me to watch this like cable TV. Do people like cable TV? Is that a positive? Are people happy to see that? I doubt that. I think that's a falsehood. Okay, why are you not... Oh my god. I apologize for being incredibly slow today, but my computer's being incredibly slow today. There we go. We now have chat. Probably. Nobody's going to be in this chat anyway, so I don't know why I was so passionate about that. Okay. Right, so today we are reading To Panic! Exclamation mark. Oh, not to panic! Exclamation mark. I'm just going to start straight out. Doubt there's going to be too many people joining in. I'm very glad to see you again, Silver Sorbet. I think it's good to just start. A bit of a thing we've done. A little bit of a refresher. We just talked about panicking, recovering from errors with panicking. Nothing that you can't really learn as you go along. Something that a Stack Overflow answer could answer better than both of these pages, which took an hour to read. However, we are now talking about panicking ourselves, creating errors in our own programs, and understanding when to create said errors, how to utilize them, and what to do with them. I'm just again going to start straight up. So how do you decide when we should call panic? And when should you return result? Returning result is just returning the result of an error to allow the program above it, or whatever is calling it, to respond to the error however you would see fit in that situation. When the code panics, there's no way to recover. You could call panic for any error situation, whether there's a possible way to recover or not. But then you're making the decision that a situation is unrecoverable on behalf of the calling code. When you choose to return a result value, you give the calling code option. The calling code could choose to attempt to recover in a way that's appropriate for the situation, or it could decide that an error value, in this case, is unrecoverable. So it can call panic. Turn your recoverable error into an unrecoverable one. Therefore, returning result is a good default choice when you're defining a function that may fail. In situations such as examples, prototype code, and tests, it's more appropriate to write code that panics instead of returning a result. Let's explore why, and discuss situations in which the compiler can't tell that failure is impossible, but you as a human can. The chapter will conclude with some general guidelines on how to decide whether to panic in library code. Examples, prototype code, and tests. When you're writing an example to hate this, it keeps coming up. You know what? I'm just going to kill it. Where is it? Where is it? You're now gone. There we go. It's gone. It's no longer going to be doing that. Web development, my boys. Alright, when you're writing an example to illustrate some concept, also including robust error handling code can make the example less clear. In examples, it's understood that a call to methods like unwrap that could panic is meant as a placeholder for the way you want your application to handle errors, which can differ based on what the rest of your code is doing. I've worked in industry, people will just copy-paste your examples anyway. Similarly, the unwrap and expect methods are very handy when prototyping, before you're ready to decide how to handle errors. They leave clear markers in your code for when you're ready to make your program more robust. Or people will do it once and never change it. If a method call fails in a test, you'd want the whole test to fail, even if that method isn't the functionality under tests. Imagine if you break the whole website. That would be very funny. Oh my lord, the entire everybody on the test just breaks because I deleted a single element. That would be incredibly funny. I hope that happens, honestly. Because panic is how a test is marked as a failure? Really? That's how it's marked as a failure? A panic. That's strange. Calling unwrap or expect is exactly what should happen. Okay. Cases in which you could have more information than the compiler. It would also be appropriate to call unwrap or expect when you have some other logic that ensures the result will have an okay value, but the logic isn't something the compiler understands. You'll have a result value that you need to handle. Whatever operation you're calling still has the possibility of failing in general, even though it's logically impossible for your particular situation. If you can ensure by manually inspecting the code that you'll never have an error variant, it's perfectly acceptable to call unwrap. And even better, to document the reason you think you'll never have an error variant in the expect text. Here's an example. Let home equal IP address 127.0.0.1.parse. Expect. Hard-coded IP address should be valid. Alright, that makes sense, because this will always be 127.0.0.1. It'll never really fail if you try and parse that. And it fails, then something really funky's happened. Perhaps the IP system has changed. Perhaps IPv4 was deprecated and we're on IPv6 everywhere now, so this fails. That's possible. We're creating an IP address instance by parsing a hard-coded string. We can see that 127.0.0.1 is a valid IP address, so it's acceptable to use expect here. However, having a hard-coded valid string doesn't change the return type of the parse method. We will get a result value, and the compiler will still make us handle the result as if the error variant is a possibility, because the compiler isn't smart enough to see that this string is always a valid IP address. If the IP address string came from a user rather than being hard-coded into the program and therefore did have the possibility of failure, we definitely want to handle the result in a more robust way instead. Mentioning the assumption that this IP address is hard-coded will prompt us to change expect, better error handling code in the future. We need to get the IP address from some other source instead. If we need to get the IP address from some other source instead. Guidelines for error handling. It's advisable to have your code panic when it's possible that your code could end up in a bad state. In this context, a bad state is when some assumption, guarantee, contract, or invariant has been broken, such as when invalid values, contradictory values, or missing values are passed to your code. Plus, one or more of the following. A bad state is something that is unexpected, as opposed to something that will likely happen occasionally, like a user entering data in the wrong format. Your code, after this point, needs to rely on not being in this bad state, rather than checking for the problem at every step. There's not a good way to encode this information in the types you use. We'll work through an example of what this means in the Encoding States and Behavior Types as Types section of Chapter 17, quite a while off. If someone calls your code and passes in values that don't make sense, it's best to return an error if you can, so the user of the library can decide what they want to do in that case. However, in cases where continuing could be insecure or harmful, the best choice might be to call panic and alert the person using their library to the bug in their code so that they can fix it during development. Alright, that does make sense. Yell at the person in the compiler. Similarly, panic is often appropriate if you're calling external code that is out of your control, and it returns an invalid state that you have no way of fixing. However, when failure is expected, it's more appropriate to return a result, rather than to make a panic call. Examples include a parser being given malformed data, or an HTTP request returning a status that indicates you have hit a rate limit. In these cases, returning a result indicates that failure is an expected possibility that the calling code must decide how to handle. When your code performs an operation that could put a user at risk if it's called using invalid values, your code should verify the values are valid first and panic if they are not valid. Alright, so if you're using unsafe code that you need unsafe code for, but it will cause unsafe behavior, then you need to check to see if it's valid before utilizing said unsafe code. Makes sense. This is mostly for safety reasons. Attempting to operate on invalid data can expose your code to vulnerabilities. This is the main reason the standard library will call panic. If you attempt an out-of-bounds memory access, trying to access memory that doesn't belong to the current data structure is a common security problem. That is a terribly written sentence. I'm sorry. Functions often have contracts. Their behavior is only guaranteed. The inputs meet particular requirements. Panicking when the contract is violated makes sense, because a contract violation always indicates a caller-side bug, and it's not a kind of error you want the calling code to have to explicitly handle. Okay, so somebody's utilizing your function in an incorrect way, and you understand said incorrect way can be done, or you can guarantee it's done in a specific way. Calling panic will force the developer to actually utilize it correctly. In fact, there's no reasonable way for calling code to recover. The calling programmers need to fix the code. Contracts for a function, especially when a violation will cause a panic, should be explained in the API documentation for the function. Hopefully that's true in the libraries or the increase.io. However, having lots of error checks in all of your functions could be verbose and annoying. Fortunately, you can use Rust type system, thus the type checking done by the compiler, to do many of the checks for you. If your function has a particular type as a parameter, you can proceed with your code's logic knowing the compiler has already ensured you have a valid value. For example, if you have a type rather than an option, your program expects to have something rather than nothing. Your code doesn't have to handle two cases for the sum and none variant. It will only have one case for definitely having a value. Code trying to pass nothing to your functions won't even compile. Your function doesn't have to check for that case at runtime. Another example is using an unsigned integer such as a U32, which ensures the parameter is never negative. Alright, and that's quite good, honestly. A lot of the time, this is an issue that happens in JavaScript. Somebody at some point passes in a null, we have no idea where the null becomes null, and so we have to go through the entire system and find out why it's becoming null in this specific case. Here, if it can become null, it won't become null, and it won't compile. There is no null in Rust. I like that. Creating custom types for validation. Let's take the idea of using Rust type system to ensure we have a valid value one step further. Look at creating a custom type for validation. Recall the guessing game in Chapter 2, in which our code asks the user to guess a number between 1 and 100. We never validated that user's guess was between those numbers, before checking it against our secret number. We only validated that guess was positive. In this case, the consequences were not very dire. Our output of too high or too low would still be correct. But it would be a useful enhancement to guide the user towards a valid guess, and of different behavior when a user guesses a number that's out of range, versus when a user types, for example, letters instead. One way to do this would be to parse the guess as an I32 instead of only a U32, to allow potentially negative numbers and add a check for the negative numbers being in range, like so. Okay, why? Okay. So right here, we're just getting the guess, parsing it to an I32. Okay, passes out the num, error continues this. If your guess is less than 1 or your guess is over 100, secret number will be between 1 and 100, and it'll continue. Okay. The if expression checks whether our value is out of range, tells the users about the problem, and calls continue to start the next iteration of the loop, and ask for another guess. After the if expression, we can proceed with the comparisons between guess and the secret number, knowing that guess is between 1 and 100. However, this is not an ideal solution. If it was absolutely critical that the program only operated on values between 1 and 100 and had many functions with this requirement, having a check like this in every function would be tedious and would definitely impact performance. Instead, we can make a new type and put the validations in a function to create an instance of the type rather than repeating the validations everywhere. That way, it's safe for functions to use the new type in their signatures and confidently use the values they receive. Listing 913 shows one way to define a guess type, though, that will only create an instance of guess if the new function receives a value between 1 and 100. So we have a struct called guess, value of an I32, implementation on guess, has a public function called new, taking in an I32 value, outputting a guess, which is this struct. If the value is between these things, if the value is not, if the value is not between these two values, we will panic with this error out. Guess value. I think that later on it's going to say, hey, this is a bad idea, we should probably return the result. Because panicking if the user puts in the wrong value will end the program and may not be a great thing. That's not a good idea. Then, of course, we return guess with value being the I32 here. Function value, just return self.value. Alright, first we define a struct named guess that has a field named value that holds an I32. This is where the number will be stored. Then, we implement an associated function named new on guess that creates an instance of guess values. The new function is defined to have one parameter named value of type I32 and return a guess. Code in the body of the new function tests value to make sure it's between 1 and 100. If value doesn't pass this test, then we make a panic call, which will alert the programmer who is writing the calling code that they have a bug they need to fix. Because creating a guess with a value outside of the range would violate the contract that guess new is relying on. Okay, what they are saying is that the calling programmer should implement a check to ensure that it is 1 to 100? That this exact code should be run every time before they create a guess on what is created outside of it? At which point I'd argue that we have just a singular additional if call here, which can be quite taxing. Of course, this is just a random example that we're trying to utilize to learn how this stuff even works, but I don't see that as being valuable in this situation. Alright. The conditions in which guess new might panic should be discussed in its public-facing API documentation. We'll cover documentation conventions indicating the possibility of a panic in the API documentation that you create in Chapter 14. If value does pass the test, we create a new guess with its value field set to the value parameter and return the guess. Okay, next we implement a method named value that borrows self, doesn't have any other parameters, and returns an I32. This kind of method is sometimes called a getter, because its purpose is to get some data from its fields and return it. This public method is necessary because the value field of the guess struct is private. It's important that the value field be private, so code using the guess struct is not allowed to set value directly, because then they could set it to 1002. That would be a bad thing. Code outside the module must use the guess new function to create a new instance of guess, thereby ensuring there's no way for a guess to have a value that hasn't been checked by the conditions in the guess new function. Of course, you can use a setter, which will have the same parameters here, just this, but it'll just change the value of guess inside the struct. I don't know how you do that in this specific language, but you know. Right, a function that has a parameter or returns only numbers between 1 and 100 could then declare in its signature that it takes or returns a guess rather than an I32, and wouldn't need to do any additional checks in its body. Yeah, it would, and it would need to do that to ensure that it got an I32 between 1 and 100. Because if the user still inputs 102, it'll crash, it'll use a panic. I mean, they describe up here why we shouldn't be doing this. Can't remember exactly where. But they literally describe that if you're utilizing user input, you shouldn't just panic. Alright, let's start this quiz. A Rust programmer is designing a library for writing command line interfaces. As a part of this library, they're implementing a function to parse command line flags provided by a user. Which implementation would be most appropriate for this domain? Right. So we have two different functions. We have one that returns a result and one which returns a string, which can panic. This is obviously the false one. We're going to read through these functions, of course, just to make sure. But a user inputs something. I believe that'll be the issue here. We should return a result here. So let's just read through this to ensure we have matching on flag.strip prefix -- so taking out any double dashes. If we have some, we have something. No underscore dash. We returned an OK with no underscore dash dot toString. So if this outputs something, we will output the string. If not, if there's nothing, we will output an error. Format invalid flag, outputting the information that we got here, which will just be a string slice. Secondarily, we have the same code up to here, which will have a none, panicking. I believe that the first one is correct. The reasoning here is that it's possible that somebody with user input fails to correctly parse or fails to correctly create the flag, or that there's just simply no flag. Thus, why should we crash if there's no flag or if they fuck up? We should pass this back to the developer to fix the issue. I believe that one is the correct one. Yep, we answered that correctly. Correct. Here, the programmer would likely want to use a recoverable error. The result: if a CLI user passes an incorrectly formatted flag, then the CLI library might want to provide additional help, like displaying the possible set of flags. A panic would force the application to only show the panic message. Bad, and would probably be a worse user experience. Definitely. Which is, again, what I'm talking about up here. I'm sorry to complain about this again, but, this does the same thing. We described this several times, and then you utilize this example and just suggest a panic here? This is incredibly dumb. This is just poorly built. Can I leave a message? I don't care all that much, actually. Right, so we got through that in record time. 28 minutes. That's going to be good stuff. Now we're going to be talking about generic types, traits, and lifetime. We're not going to get through the entire thing, but I'm glad to start it off. Okay. Sorry. Just need to respond to this message in a moment. Hopefully y'all are enjoying this. Quick one, quite easy to understand, so okay. Alright, let's start this. Generic types, traits, and lifetime. Every programming language has tools for effectively handling the duplication of concepts. First, one such tool is generic. Abstract stand-ins for concrete types or other properties. So instead of I32, it would be like a generic number. We can express the behavior of generics, or how they relate to other generics, without knowing what will be in the code. Yeah, I'm very glad, honestly. It's a differentiation between ownership. Hey, here's an absurdly complicated subject. Anyway, let's talk about panicking. I'm glad to have a bit of a break from breaking my mind. We can express the behavior of generics, or how they relate to other generics, without knowing what will be in their place when compiling and running the code. Functions can take parameters or some generic type instead of a concrete type like I32 or string. In the same way, a function takes parameters with unknown values to run the same code on multiple concrete values. Okay, in fact, we've already used generics in Chapter 6 with option T, Chapter 8 with vect, and hashmap v, Chapter 9 with result TE. In this chapter, we will explore how to define your own types, functions, and methods with generic. Okay. First, we'll review how to extract a function to reduce code duplication. We'll then use the same technique to make a generic function from two functions that differ only in the types of their parameters. We'll also explain how to use generic types and structs and enum definitions. This is quite an important chapter then. Then you'll learn how to use traits to define behavior in a generic way. You can combine traits with generic types to constrain a generic type to accept only those types that have a particular behavior, as opposed to just any type. Okay, that's good to know. Finally, we'll discuss lifetimes, a variety of generics that give the compiler information on how references relate to each other. Lifetimes allow us to give the compiler enough information about borrowed values, so that it can ensure references will be valid in more situations than it could without our help. I'm going to delete this again. Yeep. Removing duplication by extracting a function. Generics allow us to replace specific types with a placeholder. that represent multiple types to remove code duplication. Before diving into generic syntax, then, let's first look at how to remove duplication in a way that doesn't involve generic types by extracting a function that replaces specific values with a placeholder that represents multiple values. Then, we'll apply the same technique to extract a generic function. By looking at how to recognize duplicated code you can extract into a function, you'll start to recognize duplicated code that can use generic. I'm sorry for the random pauses, I've never seen somebody write in this specific way. It's quite frustrating. We begin with a short program in listing 10(1) that finds the largest number in a list. We've got a vector, which is just a list, immutable largest, which is a reference to number list 0. That's just the first element. For each number in number list, if number is greater than largest, largest equals number. Okay. So this will just go through it, and if it's larger, it'll set largest to a reference to each individual section, finding the largest. Alright, so it'll go up. We'll go up. It'll go up here. Then it'll exit. We store a list of integers in the variable number list and place a reference to the numbered list in a list and place a reference to the first number in the list in a variable named largest. We then iterate through all the numbers in the list, and if the current number is greater than the number stored in largest, we'll place the reference in that variable. However, if the current number is less than or equal to the largest number seen so far, the variable doesn't change. The code moves on to the next number in the list. After considering all the largest numbers, largest should refer to the largest number, which in this case is 100. You've now been tasked with finding the largest number in two different lists of numbers. To do so, we can choose to duplicate the code in listing 10(1) and use the same logic at two different places in the program, as shown in listing 10-2. Right, check right here, and then we check right here. However, we can extract that, just copy paste that into a function, call it, and then pass back the largest number. Although this code works, duplicating code is tedious and error prone. We also have to remember to update the code in multiple places when we want to change it. To eliminate this duplication, we'll create an extraction by defining a function that operates on any list of integers passed in a parameter. This solution makes our code clearer, expects and lets us express the concept of finding the largest number in a list abstractly. In listing 10(3), we extract the code that finds the largest number into a function named largest. Then we call that function to find the largest number in the two lists from listing 10(2). We could also use the function on any other list of i2 values we might have in the future. Alright, we just have this function largest, which brings in a list, which is a reference of i32s. A reference to a list of i32s, returning a reference to an i32. And we just do exactly what we had done before and output largest, at which point it can simply be utilized like so. Call largest the reference to the list we want to pass in. It passes out the result. Oh, we're using shadow in here too. The largest function has a parameter called list, which represents any concrete slice of i32 values we might pass in the future. I forgot, yeah, that's a slice. This is a slice. This is not a list. This is not asking for a vector or an array. This is asking for a vector slice. I did forget that, though I shouldn't, because of at and then what looks to be generically this. Okay, yeah, I should remember that. I'm trying to beat it into my head. That'll be a slice. The largest function? Yeah. In summary, here are the steps we took to change the code from listing 10.2 to listing 10.3. Identify the duplicate code. Extract the duplicate code into the body of the function. and specify the inputs and return values of that code in the function signature. Right? Copy it out to a function, figure out what needs to be passed in and what needs to be returned. Thirdly, update the two instances of duplicated code to call the function instead. Okay, that makes a lot of sense, though a lot of the time you'll think that you need to utilize it again, you'll extract it out before utilizing it the second time. You won't have two sections of code that you'll pull it out to. A lot of the time you'll just recognize that and push it in. Next, we'll use these same steps with generics to reduce code duplication, in the same way that the function body can operate on an abstract list instead of specifying values. Generics allow us to cooperate on abstract types. To operate. Sorry, I'm not speaking correctly today, but when am I ever? For example, say we had two functions, one that finds the largest item in a slice of I32 values, and one that finds the largest item in a slice of char values. How would we eliminate that duplication? Let's find out. Because a lot of this code would work for whatever. It actually just would work for whatever. That's a good point. I32, I8s, char values, any number value. And here we go. Slowly we move along. Oh, can anybody see me? Sorry, it looks like I just got heavily delayed. I don't know if there's going to be a bit of a glitch here or something like that. And I'm currently like 10 seconds behind. It doesn't really matter. I guess I'll continue on. It looks like we've caught up. Okay, generic data types. We use generics to create definitions for item. Okay, yeah, I did have a bit of a glitch. Yeah, there was a little bit of lag. Okay, looks like we're back though. Sorry about that. A weird connection today, I guess. Yeah, look at that. We got 2 bars out of the 10. Or out of the 5. I'm just going to continue though. If it does fuck up again, I'll try and stop for a moment until it gets better. Right, generic data types. We use generics to create definitions for items like function signatures or structs, which we can then use with many different concrete data types. Let's first look at how to define functions, structs, idioms, and methods using generics. Then we'll discuss how generics affect code performance. In function definitions, when defining a function that uses generics, we place the generics in the signature of the function, where we would usually specify the data types of the parameters and return values. Doing so makes our code more flexible, provides more functionality to callers of our function while preventing code duplication. Continuing with our largest function, listing 10-4 shows 2 functions that both find the largest value in a slice. We'll then combine these into a single function that uses generics. Right, so you have largest I32 and largest char. Let's see, yeah. Looking here, it looks like the code is literally the same, save for the fact that here it lists char, here it lists an I32. Here is the usage. 2 functions that differ only in their names, and the types in the signature. I'm guessing that it's just going to be like capital T here, and then capital T here, right? That'll be how we utilize the generics, unless we're creating our own. The largest I32 function is the one we extracted in listing 10.3, that finds the largest I32 in a slice. The largest char function finds the largest char in a slice. The function bodies have the same code, so let's eliminate the duplication by including or introducing a generic type parameter in a single function. To parameterize the types in a new single function, we need to name the type parameter, just as we do for the value parameters to a function. I'm sorry to keep coming back to this, but to a function? To parameterize the types in a new single function, we need to name the type parameter, just as we do for the value parameters to a function. I can't be the only one. This is very poorly written. That's not very clear what it's trying to say. You can use any identifier as a type parameter name, but we'll use t because, by convention, type parameter names in Rust are short, often just a letter, and Rust type naming convention is upper camel case. Okay, that's good to know. Short for type T, the default choice of most Rust programmers. When we use a parameter in the body of a function, we have to declare the parameter name in the signature, so the compiler knows what the name means. Similarly, when we use a type parameter name in a function signature, we have to declare the type parameter name before we use it. To define the generic largest function, place type name declarations inside angle brackets between the name of the function and the parameter, like this. Right. So largest, taking in a generic t, taking in a list, outputting a generic. We've read this definition as the function largest is generic over some type t. This function has one parameter named list, which is a slice value of type t. The largest function will return a reference to a value of the same type t. Listing 10.5 shows the largest combined function definition using the generic data type in its signature. The listing also shows how we can call the function with either a slice of i32 values or char values. Note that this code won't compile yet, but we'll fix it later in this chapter. Alright, so we got largest t. Right, so we just pulled this out, the same code inside of it, but we have called this a generic function. We have told it that it'll take any any type within a list reference and output any type. And through this code, largest will equal a reference to the first item in a list, meaning no matter what, it'll always be the type that is input. It will never output a different type than what is input. I wonder if it's possible for it to output a different type than is input, like just by accident. That would be quite frustrating. I'm very curious to see if that's possible. And we can just use it with largest both times perfectly fine, whether it's a vector or a char set. To clarify, a char set, even though it's like letters, is just a number. These will just be a number in the end. The largest function uses generic type parameters. This doesn't yet compile. If we compile this code right now, we'll get this error. Oh. Why? Yeah, I guess so. Alright. Binary operation cannot be applied to type t. Okay, because this could be a string. Any type could be a string, which you can't really, with string, say if it's larger or smaller. The issue above is that when largest takes a slice as input, the function cannot assume anything about the type t. It could be an i32, it could be a string, it could be a file. However, largest requires that t is something that you can compare with this, a greater than operator. That t implements partial ORed. Don't know what that is. A trait that we will discuss in the next section. Some types of i32 and string are comparable, but other types, like file, are not comparable. Okay, yeah, I guess so. It'll just check what all the numbers within string add up to, I assume. In languages like C++ with templates, the compiler would not complain about the implementation of largest, but instead would complain about trying to call largest on, for example, a file slice. Rust instead requires you to state the explicit capability of generic types up front. If T needs to be comparable, then largest must say so. Therefore, this compiler error says largest will not compile until T is restricted. Where do we restrict that, I wonder? Is it at the top with T? Like, hey, all things with T are restricting this way, or is it within the function signature? Additionally, unlike languages like Java, where all objects have a core method like object.toString, there are no core methods in Rust. Without restrictions, a generic type T has no capabilities. It cannot be printed, cloned, or mutated, although it can be dropped. We can also define structures to use a generic type parameter in one or more fields using the double arrow bracket syntax. Listing 10.6 defines a point struct that hold x and y coordinate values of any type. Oh, to hold. Okay, that makes sense. Not that. Sorry about that. That does make sense. Alright, so we have point with x of any type and y of any type. Function main. Let integer equal floating point. Let float equal. I don't know why I said floating point. Let integer equal point with 5 and 10. Let float equal point with 1.0 and 4.0. Alright, the syntax for using generics and struct definitions is similar to that used in function definitions. Okay, so we just kind of like jumped through this. I guess we're not going to talk about how to actually implement this at any point, are we? No, I guess we're just going to have to wait. That's really nice. I complain a lot about how this is structured, but, like, why? Why just stop at this? We don't have compilable code. We have to implement a trait. We can't, like, restrict it here. We're just going to talk... Are we going to talk about restricting it later? No, I don't think we will. I really don't think we will at any point. That is incredibly weird. Okay, fine. In this example, when we assign the integer value 5 to x, we let the compiler know that the generic type t will be an integer for this instance of point t. Then, when we specify 4.0 for y, which we've defined to have the same type as x, we'll get a type mismatch error like this. Alright, we got mismatch types right here. Expected integer, found floating point number. More information here, could not compile due to this error. Oh, I read ahead. Sorry about that. We were here. The syntax for using generics in struct definitions is similar to that using a function definition. First, we declare the name of the type parameter inside angle brackets just after the name of the struct. Then, we use the generic type struct definition where we would otherwise specify concrete data types. Note that because we've used only one generic type to define point t, this definition says that point t struct is generic over some type t, and the fields x and y are both that same type. Wonder how you could do too. Whatever that type may be, if we create an instance of a point t that has values of different types as in listing 10, 7, our code won't compile. And here's what we were stating before. I assume that the syntax would be t colon y, t colon x, as we saw in the hash map section. In this example, when we assign the integer value 5 to x, we let the compiler know that the generic type t will be an integer for this instance of point t. Then, when we specify 4.0 for y, which we've defined to have the same type as x, we'll get a type mismatch error like this. There's a mismatch error, so to reread that. To define a point struct where x and y are both generics but could have different types, we can use multiple generic type parameters. This example, For example, in listing 10-8, we've changed the definition of a point to be generic types over T and U, where X is the same type T and Y is of type U. Here we go. We just bring it in 10, U, and set that to T and Y. Unlike here, where they're both T. Does this allow it to be the same type? Yes, it does. Both integer, 5, 10, both float, 1.0, 4.0, and here's some mix. Now, all the instances of point shown are allowed. You can use as many generic type parameters in the definition as you want. Using more than a few makes your code hard to read. If you're finding you need lots of generic types in your code, it could indicate that your code needs restructuring into smaller pieces. This is a very common, nice way to say, maybe you should rethink what your life choices have been up to this point now. And enum definitions. As we do with structs, we can define enums to hold generic data types in the variance. Let's take another look at the option T enum that the standard library provides, which we used in chapter 6. Enum option of any type, some of any type, or none. This definition should now make more sense to you. As you can see, the option T enum is generic over type T. It has two variants, some, which holds one value of type T, and none, and a none variant that doesn't hold any value. By using the option T enum, we can express the abstract concept of an optional value. And because option T is generic, we can use this abstraction no matter what the type of the optional value is. Enums can use multiple generic types as well. Definition of the result enum that we used in chapter 9 is one example. Yep, there we go. Right, OK of any type, or E, error of any type, but we're also calling it type E. The result enum is generic over two types, T and E, and has two variants, OK, which holds a value of type T, and error, which holds a value of type E. This definition makes it convenient to use the result enum anywhere we have an operation that might succeed, return a value of some type T, or fail, return a value of some type E. In fact, this is what we use to open a file in listing 9.3, where T has filled in the type standard, file system, file. When the file was opened successfully, and E was filled in with the type standard IO error, when there were problems opening the file. Okay, sure. When you recognize situations in your code with multiple struct or enum definitions that differ only in the types of the value they hold, you can avoid duplication by using generic types instead. In method definitions, we can implement methods on structs and enums as we did in chapter 5, and use generic types in their definitions too. Listing 10-9 shows the point struct we defined in listing 10-6, with a method named X implemented on it. X and Y gotta be the same type. Implement point T, X, taking in a reference to self, returning a reference to T, return self.x. Okay. I'm sorry, I guess I really don't understand exactly what's going on here. Oh yeah, the function. Yeah, this is just a getter function. Sorry about that. Bit tired, didn't exactly get that. This is just a getter, which will get X. Struct that will return a reference to the X field of type T. Oh, that'll return a reference. Sorry. Here we've defined a method named X on point that returns a reference to the data in the field X. Note that we have to declare T just after implement. We can use T to specify that we're implementing methods on the type point T. Oh, I didn't notice that. Yeah, that's what we're trying to state. Implements on any type, point of any type. By declaring T as a generic type after implement, Rust can identify that the type in the angle brackets. Sorry, just a moment. I forgot to close that again. I just leaked my IP address twice in a row. Sorry about that. By declaring T as a generic type after implement, Rust can identify that the type in the angle brackets in point is a generic type rather than a concrete type. We could have chosen a different name for this generic parameter than the generic parameter declared in the struct definition, but using the same name is conventional. Methods written within an impl that declares a generic type will be defined on any instance of the type, no matter what concrete type ends up substituting for the generic type. Okay, so that's actually quite useful. We can define something only if it's a specific type. Perhaps there's some bit of code that'll only work if something's a float, like divided by 2, which could put like 0.5 out, and you only want to implement that on things that are of type float. But here, we are implementing it on any type within point. Alright, that does make sense. You can also specify constraints on generic type when defining methods on the type. Could, for example, implement methods only on F32, as I was talking about. Instances rather than point T. Instances with any generic type. In listing 1010, we use the concrete type F32, meaning we don't declare any types after implement. Yep, so implement point F32. Alright, so we just got distance from origin, output F32, self x Howie. Well, that's nice. 2 self.y Powie 2.squirt. This code means the type point F32 will have a distance from origin method. Other instances of point T where T is not an F32 will not have this method defined. The method measures how far our point is from the point at coordinates 0, 0, and uses mathematical operations that are available only for floating point types. You cannot simultaneously implement specific and generic methods with the same name in this way? Why not? For example, if you implemented a general distance from origin for all, that makes sense, yeah. For all types T and a specific distance from origin for F32, then the compiler will reject your program. Rust does not know which implementation to use when you call this. Alright, that makes sense. Sorry, I thought it meant like if you used one generic, you could not use any other implementation with a generic, or with a specific, but no, if you have distance from origin of type T, which is any type, or distance from origin for type F32, you don't know which is which. Could you implement one that's for everything with the exception of F32? And then a separate one for F32? I suppose you'd have to implement it like 13 times for every single type that would meet the behavior. Well, I guess that's kind of complicated. There's probably a solution eventually. I doubt it'll actually discuss it in this book, though. That's probably not something you're ever going to run into. More generally, Rust does not have inheritance-like mechanisms for specializing methods as you might find in an object-oriented language, with one exception, default trait method, discussed in the next section. Generic type parameters in a struct definition aren't always the same as those you use in that same struct's method signature. Listing 10-1 uses the generic types x1 and y1. The Rust for the point struct and x2, y2 in the mix-up method signature to make the example clear. The method creates a new point instance with the x value from the self point of type x1 and the y value from the passed-in point of type y2. I'm sorry, I don't fully understand this. I really just don't understand exactly what's going on. Apologies, but I am going to reread this. Generic type parameters in a struct definition are always the same as those you would use in the same struct's method signature. Listing 10-1 uses the generic types x1 and x2 for a point struct and x2 and y2 from the mix-up method signature to make the example clear. The method creates a new point instance of the x value with the x value from the self point of that x1 and the y. Right, okay. I am sorry, I don't fully understand this. Oh, I think I understand. Okay, so just to make this clear that this is a different type, or this is a different value, I guess. So function mixup, taking in a different value, which takes in self another point with those same values, outputting a point with something from the original, the secondary. Yeah, I got it. Thank you for that. Okay, I think I got it. Yeah, that makes sense. We have x, which is self.x, and y, which is other.y. Sorry, I'm tired. I barely know what I'm doing anyway. Ah. Okay, and then we have the implementation where we just have 1, 2. We have p1.mixup 2, which will output, that'll output 5c. Right. In main, we've defined a point that is an i32 for x with the value 5 and an f64 for y with value 10.4. The p2 variable is a point struct. Sorry, there's some important things I gotta. Never mind, that was just my VPN reconnecting. Sure. Right. And then, yep. The p2 variable is a point struct that has a string slice for x with value hello, and a char for y with value as c. Volume mixup on p1 with the arguments p2 gives us p3, which will have an i32 for x because x came from p1. The p3 variable will have a char for y because y came from p2. Printline macro will call print. The printline macro will call print the x equals 5, the y equals c. Sorry, this is poorly written. The printline macro will call print p3.x equal 5. It's not calling print px equals 5, p3 equals, py equals c. That's incredibly unclear language. I believe these do go to a person, but I don't think they're going to read this. The purpose of this example is to demonstrate a situation in which some generic parameters are declared with implement, and some are declared with the method definition. Here, the generic parameters x1 and y1 are declared after impl because they go with the struct definition. The generic parameters x2 and y2 are declared after function mixup because they're only relevant in that method. That makes sense. Performance of code using generics. You might be wondering whether there is a runtime cost when using generic type parameters. The good news is that using generic types won't make your program run any slower than it would with concrete types. I wonder if it compiles slowly. Rust accomplishes this by performing monomorphization. What? That's going into the read list of the code using generics at compile time. Monomorphization is the process. You're going to have to go? Alright, not an issue. I am going to continue to the end of this. It's quite soon. But I guess I'll stop at this point. Thank you for being here and have an excellent day. Alright. Monomorphism is the process of turning generic code into specific code by filling in the concrete types that are used when compiled. In this process, the code does the opposite of the steps we use to create the generic function listing 10.5. The compiler looks at all the places where generic code is called and generates code for the concrete types the generic code is called with. Let's look at how this works by using the standard library's generic option. We have let integer equal sum5, let float equal sum 5.0. When Rust compiles this code, it performs monomorphization. I still don't know what that is. In programming languages, monomorphization is a compile-line process where polymorphic functions are replaced by many more monomorphic functions. What the fuck is a monomorphic? Or one singular morphic? There's one singular way it can morph, change. For each unique instance, it is considered beneficial to undergo this method transformation because it results in the output indeterminate representation having specific types, which allows for more efficient optimization. Oh, okay. Additionally, many IRs are intended to be low level and do not accommodate polymorphism. The resulting code is generally faster than dynamic. Okay, I think I understand what's going on. So it looks to your code and just recreates the function for every single type possible during compilation. So it'll make your function for floats, it'll make your function for integers, etc., instead of at runtime having to run different code based on that. Alright. Values have been using the option T instance and identifies two kinds of option T. One is I32 and one is F64. As such, it expands the generic definition of option into two definitions specialized. It is specialized to I32 and F64, thereby replacing the generic definition with a specific one. Okay, so it is legitimately just replacing our generic code with two or more functions, which could be anything, which are specifically integer and float. That makes a lot of sense. It allows us to program in a way that's quite minimized in the amount of code. It allows us to change it only in one place, but doesn't lose the performance benefits from having each specific piece. I'm assuming that this happens in a lot of other programming languages, but I've honestly never even thought about it. The monomorphized version of the code looks similar to the following. The compiler uses different names than what we expect here for illustration. Option I32, option S64, brings in I32 and 64, main integer option I32, sum 5, sum 0. Alright, so that's how it works when it changes the code pre-compilation. So this is pre-compilation. This will be before it starts compiling. Generic option T is replaced with the specific definitions created by the compiler. Because Rust compiles generic code into code that specifies the type in each instance, we pay no runtime costs for using generics. When the code runs, it performs just as it would have if we duplicated each definition by hand. The process of monomorphization makes Rust generics extremely efficient at runtime, though probably pretty inefficient at compile time. Well, honestly, I don't think this is too inefficient. It'll add a bit of time, but not a lot. Imagine using imagine using a third-party function. Yeah, that's correct. Imagine using a third-party function whose implementation you don't know, but whose type signature is this: mystery T, X T, output T. Who knows? Then you call mystery like this. Assuming mystery uses no unsafe code, then the value y must be an integer, an I32, or 3. What? Alright, imagine using a third-party function whose implementation you don't know, but whose type signature is this. We have x, which is of type t, and we're returning something of type t, and it does something random. Then you call mystery like this, let y equal mystery 3. Assuming mystery uses no unsafe code, then value y must be an I32. This is poorly written, incredibly poorly written. It's asking for the value, which we have no idea. It could multiply this by 2 and the value could be 6. Y might be 6. Oh, no. Y might be 6. Why couldn't y be 6? Then the value of y must be 3? This is incredibly frustrating. What in the world is it even asking? What? The value of y must be, let's say, 3, because the value would have to be... Is there something I'm not getting? It's not asking for a mutable x. But it could check if it's below 100. The mystery could be to check if it's below 100 and list out 43 if it is. It could be outputting something else that's not like a reference to anything. I'm going to say it's looking for us to put in I32. Right, will this program compile? We have P, V of a reference to a slice vector of call V, or X in V print X. I see no issue here. And we have a reference to a slice vector here. I think this will compile. I see no reason why this won't compile. Yeah, I see no reason why this won't compile. It can be any type. It can be, doesn't output anything. It actually doesn't output anything. It doesn't mutate anything. That's fine. So that'll output 1, 2, 3. 1, 2, 3. Yep. That's fine. Determine whether the program will pass the compiler. If it passes, write the expected output of the program if it were executed. Right, we have implement point I32, F, it takes in self, returns an I32, it just outputs Y. Just outputs Y. That's correct, that's correct. That'll be implemented on anything which is only an I32. This implements on anything that's generic. No, that won't compile. That will compile because we have a function called f that is a in a generic and b in an I32. That will not compile. 1 of 3 corrections are correct. What are we talking about? So it is 3. It's looking for 3? What are you talking about? Let's just see the... 3! What? No, it won't. The only possible function without unsafe code that has the signature T, returning T, is the identify function. Really? The function could of course panic or print, but the return value can only be the input. Can it only be the input? Why? Could it not just output like 7? Right, I'm going to check this out. Slash, right, actually, let's just go into here. Let's just go into the here. Cargo. New. Checking out. CD. Checking out. Right, now under source, under main, let's create this. Right, so we have a function. Which will simply output 4. Expected type parameter T. Found integer. Oh, I see. I see what's the problem. I see where I got that wrong. Okay, I'm glad that I checked this. Instantly figured out why. Because 4 could be of one type, I32. It cannot... Right, I understand. I do understand now. So the issue here is that this takes an any type and returns any type. So how do we output something that is any type, when the only thing we have is x of any type? Could we not just do x plus x? Yeah, okay. Yeah, that's fair, because there could be a file, which we can't add a file to a file, can we? So, that won't. Okay, yeah, I can see that. I can see that now. I feel sad. Does not know what type T is. Right. The function could of course panic, but the return value can only be the input. Mystery does not know what type T is, so there is no way for Mystery to generate or mutate the value of T. See theorems for free for more examples of this idea. Alright, now I feel kind of embarrassed. That is a bit dumb of me. A little bit of a stupid thing for me to have done. 3 is really the correct answer. If you disagree with the answer, please don't submit our bug report. Okay, so I guess they got a lot of people like me who are quite angry and thinking about doing that. 3 is really the correct answer. Okay. I'm wrong on this. Just entirely wrong. That's good to know. Sorry for wasting you guys' time if you're listening to this. Right, what did I get wrong here? Program does not compile. Okay, I did get that wrong, that's fair. If a type is generic, like T, well, let's just start looking at this. Alright, so we got T, T. I really don't see the issue here. We aren't returning anything, that's not the issue. We may not be able to iterate. That might be the issue. Could we not iterate? Why would we not be able to iterate? We should be able to iterate, but we might not be able to print it, because if this is a file, we may not be able to print. Is that the issue? We cannot assume anything about it, including the ability to turn it into a string. Alright, okay. Therefore, print line is invalid because X is a reference to T. I did get this one right. It does not compile, and it will state the same here. These definitions of F conflict, and there is no way for us to determine which F should be used when P.F is called. Therefore, this is a compiler. Alright, that makes sense. Right, so what this is trying to point towards us, what this is trying to teach us, to be very careful of what we do, and that we have zero assumptions of what could be input when utilizing a generic. Unless we use some trade or some way to make sure that it is of that type, don't do anything with it. Don't do anything with it that you couldn't do with anything, I guess. With any different piece of information. I guess just pure generics are kind of useless for any actual work, because you can't work on them without assumption. Alright. Well, as stated, I think this is where we're going to end for today. Thank you all for joining me, but I am going to end. Tomorrow, or in a week from now, we will be doing traits defining shared behavior. This is likely where we will be learning how to do the things which we got in the previous chapter.